Bulldogs. So here we are, we're talking about how we're going to fight using z-scores. So someone makes a claim, we want to prove that claim right, or we want to prove it wrong. Last time we learned about z-scores using a single point, so you've got one piece of data, you're just looking at your sister, just looking at your brother, just looking at one instance with a car, just one set of data. One data point compared to the one set of data. Today what we're going to do is we're going to take a sample and compare it to the population, or compare it to a claim. So throughout today we're going to use an example, a claim. Let's say that the claim that we're going to be using Burbank High School students are on average 62 inches tall. Okay. That is the claim, that's the statement. So that's the null hypothesis. Mus of 1, mus naught is equal to 62 inches. So the alternative hypothesis today is mus of 1 does not equal 62 inches. Okay? Alright, well, let's go through some of these. When we are going to be comparing a sample to the population, we need to first determine, is it normal? Is it normally distributed? Remember, normal distribution kind of looks like that. There's a rise in the middle, everything's kind of evenly distributed on either side. An example of what would not be normally distributed would be that. That is not a normal distribution. That is not a normal distribution either. Okay? Normal distribution, one hump, one mound, that's a normal distribution. Let's go, so the other assumption is that your sample size, n, is at least 30. You've at least taken 30 samples before you're going to go to court and compare with the claim that was presented. Okay, so your sample size is n. I would suggest writing this down. N is your sample size. Mu is your population average, or the average that you've been given before you do any testing, okay? That's the population that's given. That's what you're trying to say is either right or wrong. Your standard deviation. X bar, your sample average. Then finally, your sample standard deviation is going to actually be a formula. It is the population standard deviation divided by the square root of n. Okay. So with using these, we are going to be able to go through, take a sample, use this formula here, which you should probably write down. It's the sample average minus the population average divided by the sample standard deviation. Okay. You go through, you're going to calculate your numbers, you're going to get your p-value, you'll get your answer. We'll do a problem here in a sec. Okay? This is the formula that we're using when it's a sample. You're using the sample average. When it's just a single point, you're just using a single point. You can't have a standard deviation with just a single point. So you end up using the population standard deviation. However, with the sample, you do end up getting a standard deviation. So here we use the sample standard deviation. Okay, pause it. Here we're going to compare the sample average to the population average. So the school's saying that the average is 62 inches tall. You go through and you get a sample of 32 people, and the average is 65 inches tall. Well, who's true? What's the truth here? Okay, the sample standard deviation is the population standard deviation is 35. Now, the school is saying that it is 62 inches tall. So that's our null hypothesis. If we're wrong, then nothing exciting happens. However, if we're right that it's not 62 inches tall, that means that it could either be greater or less than. So that must be the alternative hypothesis, because that's a little bit more exciting. Something's happening. The school isn't right. So we have that as the alternative hypothesis. Okay, is this a one-tail or a two-tail test? This is a two-tail test. How can we know? It's because it does not equal. So the actual answer could be greater than, or it could be less than the actual average. So in this case, if 0.05 is our alpha, and we're splitting that between two tails, we're getting 0.025 over there, and 0.025 over here. Okay, both tails have an area of 0.025. Okay, let's go through and calculate our sample standard deviation. So our sample standard deviation is the standard deviation divided by the square root of n. Guys, you can pause if you need to and write stuff down. Or rewind and listen to me say it again. Standard deviation is 3.5. N was 32. Remember, n is how many people had in my sample. So 32, that's roughly 2 class sizes this year because of COVID and everything that's going on. Any other school year, it'd probably just be 1 class size or even smaller than an entire class. So we sample an entire class. I'm going to figure out the sample standard deviation. That gives me 3.5 divided by the square root of 32. 0.618. Okay. We've got our data. Awesome. Now I can go through and plug it all in here. Remember, X bar is your sample average, not the population average. Population average is mu. Standard deviation of X. We already calculated that. So when we go through and do this, we've got 65 minus 62 divided by 0.618. Now this is assuming, these 32, that they are randomly chosen from the school. Okay? It does have to be random. You can't just go around and pick the tallest 32 people in the school to make your argument. You have to randomly choose those people. Okay, here we go. 65 minus 62, that's 3. 3 divided by, that is 4.84. That is our sample standard, our z-score. Now, we go through, we use a p-value to figure this out, and we get a p-value of, what is that going to be? 0.9999. Alright? That's our p-value. Well, if we come over here, all we had to do was get past 0.975. We got all the way up to 0.9999. So do I keep or do I reject my null hypothesis? It's in the little tail. It's in the shaded area. So we reject the null. Okay, we reject the null hypothesis. That means that we are very, very sure that the average is not 62. The average could be 62 and a half. Average could be 63. We don't know if the average is 65. We are just extremely, extremely sure, not 100% sure, but we are extremely sure that the average is not 62. That we are sure about. All right, next problem. Let's look at what the school is claiming. The school is claiming that every student has at least $100. So, doing a field trip or whatever, the kid can afford their own way. Every kid has at least $100. Not a big deal. We want to prove the school wrong. It's tilted a little. Is that any better? It's a little bit better. Okay. We want to prove the school wrong. We want to prove, we don't all have $100. And then, here's our sample size, yada, yada, yada. That's what we're trying to prove. We're trying to prove that we don't actually have $100 each. The school says that we all have at least $100 on average, but we're all saying, no, we don't. No, we don't. So, is this a one-tail or a two-tail test? This is a one-tail test. We're just trying to prove that it could be less than. We don't care about less than or greater than. We just care less than. So we've got our data on this side. Awesome, awesome. The shaded values over here. So we don't have to worry about splitting alpha. Alpha is strictly going to be one value. Okay, so the average is 100. The standard deviation was 200. We're claiming that it's less than. We go through, we take a sample. Our sample average was 80. That's less than, so we're heading in the right direction. And we took a sample originally of 30 people. So the first sample we did was of 30 people. Let's see if that was enough. Okay. We go through and calculate our sample standard deviation. That is 200 divided by the square root of 30. That's going to give me about, what was it, 15, 18, somewhere in there. 200 divided by the square root of 30. Oh, sorry, 36.51. So $36.51 is the sample standard deviation. Well, let's go through and calculate the rest of this now. So it is the z-score of x bar minus mu divided by the standard deviation of the sample. So x bar is 80 minus 100 over 36.51. Let's see what we get. Let's see here, negative 20 divided by 36.51. That gives us a z-score of negative 0.55. And the p-value for that would be 0.2912, which puts us right there. Is that enough to reject our null hypothesis? It is not enough to reject the null hypothesis. We can't get rid of this school statistic. Okay, we're stuck with it if we're sticking with this data. But there is something that we can change. We can't change really what our sample average is going to be. That's just going to be whatever it is. You can't change the population statistics. But what you can do is you can go out and get more samples. So let's say we go out and we've got 500 people now in our second sample. We go out, sample a lot more. We get 500 people. We randomly sampled people. Okay, it's not just going up to your friends. It's not just going up to people that you know have money. It's not just sitting outside a fancy restaurant asking people how much they have as they come in. It's not just asking people over at the vending machines. It's randomly asking people. Okay, so we're going to use the same setup, but we need to calculate the new sample standard deviation. The new sample standard deviation with 500 would be 200 divided by the square root of 500. That gives me 8.94. Okay. This was sample standard deviation with just 30. Okay. So let's plug that in. We've got 80 minus 100 over 8.94. Let's see if having more people helps our argument at all. Because our sample, let's just say it stayed the same. 80 is less than 100. We don't know what the actual population average is, if it is less. But we're trying to prove that it's less. We're trying to prove the school wrong. So we've got negative 20 divided by 8.94. That gives me a z-score of negative 2.23. All right, negative 2.23. The p-value for that, 2.212. The p-value is 0.0129, which would put us right about here. By having a larger sample, are we able to prove the school wrong? Yes, we can. We can go in, we have a lot of data now. We have 500 data points that all suggest that the average is less than $100 per student, okay? With a p-value of 0.0129. When we just had a smaller sample of 30, you can see the p-value wasn't as promising. Yeah, it was less than 100. The average was less than 100, it was 80. But it wasn't as convincing. We didn't have enough people to really prove it. But once we get 500, you figure the school population is only, what, 1,200? So once you've sampled half the people, at that point, yeah, you've got a pretty good idea of what the actual population is going to be. So the larger your sample is, the more convincing your data will be to whoever you're presenting it to. I'm going to do one more example. If you need it, great. If you don't, whatever. End the video. All right, third problem. Last example for this. So Java Juice, they're selling their drinks, and they're saying, you know what, we've got 18 grams of sugar in each of our cups. Well, I go over and I buy my Java Juice. I don't even know what Java Juice is. But I go over and buy my Java Juice, and I do some tests, and I realize it only has 14 grams of sugar. Are they telling the truth, or are they not? So over the course of 42 days, as I go and get my Java Juice every day, I test how much sugar's in it every single day, and I come up with an average of those 42 drinks, an average of 14 grams. So over 42 days, I'm getting an average of 14. They're saying that there should, on average, be 18 grams of sugar. Are they shorting me on sugar? And do I have enough information to tell? The standard deviation should be about 5 grams. Well, is this a one-tell or a two-tell test? So the thing here is we have to look at what the null hypothesis is. The null hypothesis is the average is 18 grams. They're not saying our average, well, we put in at least 18 grams of sugar, or we'll put up to 18 grams of sugar. No, their average is 18 grams of sugar. That is what they are guaranteeing you as a customer, 18 grams of sugar. So the alternative hypothesis is they're lying. They're not really giving us 18 grams of sugar. We're going to start a lawsuit. Okay? That's what we're going to do. So, one-tell or two-tell? This is a one-tell test. Alright? This is a one-tell test. Sorry, whoa, what am I talking about? This is a two-tell test. I'm sorry. I am horribly sorry. This is a two-tell. It could be more than the mean, it could be less than the mean, okay? It could be greater than or less than, just not equal to. Okay, if we have an alpha of 0.05, then that means the p-values we are looking for are going to be less than, what's half of 0.05? 0.025. So we're looking for p-values less than that, or p-values greater than, what's 1 minus that? It'd be 0.975. Okay? We're looking for p-values that are in this area. If we can get a p-value in that area, we might have a lawsuit on our hands. Ooh. Okay, well, let's go through and do some tests. First, we need to figure out our sample standard deviation. Our sample standard deviation is going to be 5 divided by the square root of 42. That gives me 5 divided by the square root of 42, 0.771. Well, let's calculate. Z is our average, sample average divided by the population average. Sample average minus the population average divided by the sample standard deviation. Okay, we've got that. We're going to go through now. Plug in our numbers. That's 14 minus 18. Divided by 0.771. That gives me -4 divided by 0.771. 4 divided by 0.771 is a z-score of negative 5.18. And that's going to give me a p-value, if you look it up, of 0.0001. Okay? Where does that fall? That falls way over here. Do I have enough information to file a lawsuit? I do. So, based off the evidence that we've collected, showing that our p-value is less than the alpha, we can reject the null hypothesis. Ta-da!